Detecting the second event is terrific because it's not just detection of gravitational waves now that we're engaged in, it's gravitational wave astronomy and astrophysics. We believe that this means we're now going to see a whole family of black hole systems out there, and that means we can start to do astronomy, astrophysics, probe the properties of the black holes, and actually use that to tell us more about the way the universe got to look the way that it is now.
The second detection was of a system very similar to the first detection. It was two large black holes, total mass about 22 times the solar mass, and these coalesced and produced a flash of gravitational waves, very similar to the waves we saw last time, but this time we saw them for about 1.2 seconds rather than 0.2 seconds. Well, we saw this signal on the 26th of December of last year, so just after Christmas. It was a nice Christmas present. And the event itself, though, happened about 1,000 million years ago. We can't say precisely, but round about then. And at that time, the Earth was uninhabited in any normal sense. All we were then were amoebae. So that was the time in the past when this event happened. But of course, the signals have been travelling towards us since then. One of the things we have seen in the second detection, which we didn't really see in the first one, we saw the spins of these black holes as they orbited each other and came together into that final black hole. And that's important because the directions of those spins tell us something about the origins of those black holes. If they were aligned like this, then maybe they formed in a system together. If they're randomly oriented, then maybe these are black holes which just happen to come together.
For us, that's a terrific vindication of all the effort we've put into getting the gravitational wave detectors on the ground to the state that they're in at the moment, able to make now multiple detections. Later this year we hope to run the detectors again for longer with some improved sensitivity, and that's going to be a particularly exciting time.
Looking a decade or so ahead, we hope to have even more sensitive detectors on the ground, and perhaps 20 years from now, we're pretty confident that we'll also have a spaceborne detector building on the remarkable success of LISA Pathfinder, pointing us towards how we might do that. So that means we'll be in a position to probe gravitational waves across the whole spectrum of gravitational waves. Just like we do with light, we look at stars, we look at galaxies, all the way from X-rays and gamma rays to radio waves. We'd like to do the same with gravitational waves. It's an area that we've got quite a track record in Glasgow of studying, using observations with light of astronomical objects, everything from stars to galaxies to asteroids, working out from what we see what the underlying population of objects out there in the universe is truly like, and in particular to try to join the dots between the stellar mass black holes that we've detected with advanced LIGO and the supermassive black holes that will be the principal target for LISA, which is the full spaceborne mission that we hope will now follow on from LISA Pathfinder. So understanding the role of those stellar mass black holes in making supermassive black holes is going to be a key question for gravitational wave astronomy in the decades to come.